Objects at rest want to stay at rest. Objects in motion want to stay in motion. Okay, this is a simple way of stating Newton's first law of motion. It's the law of inertia. So let me show you a way we can take advantage of Newton's first law, this law of inertia, to determine an unknown mass. Let's say I wanted to know what's the mass of this stapler, but I don't have a proper scale that's already calibrated for me. I could make my own sort of scale that tunes into the inertia of the object. See, this empty pan is at rest, so it wants to stay at rest. When I pull it back ever so slightly in this direction, a force shows up due to the tension in this beam. So when I let it go, that force is going to overcome the inertia of the empty pan and make it start to accelerate in this direction. Now, for a split second, it's going to accelerate back to that equilibrium point where there is no force in these beams. But it's developed some velocity, and so now the object in motion wants to stay in motion. And so it carries past the equilibrium point, and now the beams bend in the other direction and apply a force back this way. So it causes it to have a constant acceleration back and forth, and what that results in is a frequency, which is saying how many times does it vibrate in 1 second, or we can think of it as the inverse of that, what we call the period. How much time does it take for one there and back full oscillation? And so here's what I do. I just let it go and measure the period. Now here's where I get tricky. I take a known amount of mass. This is exactly 500 grams. And I place it in the pan. I pull it back a little bit. You can hear the frequency to it, and we could certainly make a direct measurement of the period. Maybe what we would do is measure the time it takes for 20 vibrations, and then just divide that time by 20, and then that would be the time it takes for one full vibration. Okay, now I put in even greater mass. Well, Newton's second law tells us with even more mass comes less acceleration, so the frequency should go down, and therefore the period, the time it takes for a vibration, goes up. So let me show you. I'll pull it back here. Yeah, now it's accelerate even less, right? Take one of them out. The period becomes a little smaller. Take them all out, and the period becomes quite a bit smaller. So you can see where I'm going with this. We can use that information to make a graph of sorts. So probably what we want to do is put the changing amount of mass on the x-axis, and then we'll graph how much time does it take for a full vibration. We'll compare the period of oscillation to the mass. And we have a few data points. We say, okay, at 500 grams, it took a given amount of time. With 1,000 grams, it took some given amount of time. And with enough data points, we might find that that reveals this curved shape. So the last step is to take the object whose mass we want to determine. So back to our stapler, put it in here, pull it back, and then just measure how much time does it take to complete vibration. So we go back to our graph, and by direct measurement, maybe we find that, oh, it took about that much time for a full vibration in the case of the stapler. So I read across, find where it intersects the curve I generated with the other data points, and read down, and there we would have it. We reveal the mass of the stapler in this way. So this is just sort of a clever way to use Newton's first law to determine the mass of an object.